Welcome back to Boring Astronomy. This time, we explored the vast, widely dispersed, and surprisingly boring expanse of the asteroid belt. Not a chaotic minefield, but a quiet collection of cosmic remnants, held in predictable orbits, offering a silent archive of our solar system's early days. Tonight, we're going to shift our perspective entirely. Instead of looking outward into the vastness of space, we're going to turn our gaze inward, far beneath our feet, and embark on a quiet, fascinating journey to the very heart of our planet, Earth's core. This isn't a place of dramatic cosmic events or glittering stars. It's a realm of unimaginable heat, immense pressure, and constant, quiet activity, profoundly hidden from our view. Yet, its seemingly inaccessible and utterly boring internal processes are absolutely vital for life on our surface. So, dim the lights, perhaps turn on a fan for that soft hum, and let's ease into tonight's journey together. You walk on the Earth's crust every day. You might dig a hole, or a mine might extend a few kilometers down. But what lies hundreds, even thousands, of kilometers beneath your feet? The answer is a series of distinct layers, much like an onion, each with its own characteristics, contributing to the overall stability and habitability of our planet. The outermost layer is the crust, thin and brittle, where all life exists, ranging from about 5 to 70 kilometers thick. Beneath that is the mantle, a thick, mostly solid, but plastically flowing layer of rock, extending down to about 2,900 kilometers. And then, at the very center, is the core. Unlike the surface of the Moon or the plains of Mars, which we can observe directly or land spacecraft upon, the Earth's core is utterly inaccessible to us. We can't drill down to it. No material known to science could withstand the extreme temperatures and pressures. So, how do we know anything about it? This is where the truly boring, yet incredibly powerful science of seismology comes in. When an earthquake occurs, it generates seismic waves that travel through the Earth. These waves behave differently depending on the material they pass through. They speed up, slow down, or are reflected and refracted at boundaries between different layers. By meticulously studying the precise travel times and paths of these waves from earthquakes across the globe, scientists can create a detailed picture of Earth's internal structure, exploring the composition, temperature, and even the state of its hidden layers. It's detective work on a planetary scale, relying on the predictable physics of wave propagation, a constant, silent echo from within our planet. The Earth's core itself is divided into two main parts, the outer core and the inner core. Let's start with the outer core. This layer, about 2,300 kilometers thick, is composed primarily of liquid iron and nickel, along with some lighter elements. The temperatures here are extreme, ranging from around 4,400 Celsius at its outer edge to about 6,100 Celsius at its boundary with the inner core. To put that in perspective, parts of the outer core are nearly as hot as the surface of the sun, that great power source we explored a few episodes back. But unlike the sun, which glows brilliantly, the outer core is a hidden liquid inferno, silently churning. And it's this churning that makes it so profoundly important. The liquid iron and nickel in the outer core are constantly in motion, driven by convection currents. Hot, less dense material rises, cools, and sinks, creating vast, slow-moving eddies. Because these metals are electrically conductive, this convective motion generates electric currents. This is the geodynamo at work, the boring, continuous process that generates Earth's powerful magnetic field. And as you might recall from basic physics, moving electric currents create magnetic fields. It's a silent, unseen powerhouse, perpetually generating the force field that defines our planet. This isn't a dramatic, visible process. It's a constant, fundamental, geophysical phenomenon happening right beneath our feet. Now, let's descend further to the very center, the inner core. This is a solid ball of iron and nickel, about 1,220 kilometers in radius, roughly the size of the Moon. Why? because of the immense pressure. The weight of all the overlying layers of Earth is so extraordinary that it crushes the iron atoms into a solid crystalline structure. Even at these unimaginable temperatures, this is a fantastic demonstration of how pressure can overcome heat, a boring but fundamental principle of physics. The inner core isn't static. Seismic studies show that it actually rotates slightly faster than the rest of the Earth, about 0.2 to 0.7 degrees per year more quickly than the mantle and crust. This seemingly small, almost imperceptible difference in rotation over a year might seem boring, but over millions of years, it can lead to a significant difference in orientation relative to the surface. Furthermore, the inner core is slowly, imperceptibly growing. As the Earth gradually cools over billions of years, liquid iron from the outer core solidifies onto the surface of the inner core. It's a continuous, glacial process of crystallization, adding new layers to the planet's solid heart, a testament to the long, slow geological evolution of our world. So, why is this hidden, hot, dense, and seemingly boring core so vital to us on the surface? Its importance is multifaceted and profound. Firstly, and perhaps most crucially, is the Earth's magnetic field. This field, generated by the geodynamo in the outer core, extends far out into space, forming a protective bubble around our planet called the magnetosphere. This magnetosphere acts as a gigantic, invisible shield against the harsh realities of space. It deflects the constant stream of charged particles from the sun known as the solar wind, as well as more energetic cosmic rays from deep space. Without this magnetic field, the solar wind would gradually strip away Earth's atmosphere, just as it is believed to have stripped away much of Mars's atmosphere over billions of years. Life as we know it, protected by that crucial atmospheric blanket, would be impossible. So, every time you use a compass or witness the beautiful auroras at the poles, you are seeing the direct, boringly consistent work of our planet's core. Secondly, the core plays a fundamental role in plate tectonics. The immense heat generated in the core and radioactive decay in the mantle drives convection currents within the Earth's mantle. This slow, churning motion of solid rock in the mantle, happening at speeds comparable to the growth of your fingernails, is what causes the Earth's rigid outer plates to move, collide, separate, and slide past each other. This seemingly boring geological process is responsible for virtually all the dramatic geological features we see on the surface: the formation of mountains, the opening and closing of ocean basins, the occurrence of earthquakes, and the eruption of volcanoes. While these events can be dramatic, they are all ultimately symptoms of the core's long-term, consistent heat output, the silent engine of our dynamic planet. Plate tectonics also plays a vital role in regulating Earth's climate over geological timescales, participating in the long-term carbon cycle that keeps our atmosphere balanced. Finally, the immense mass and density of the core contributes significantly to Earth's overall gravitational pull and stability. Its presence helps to anchor the planet and ensures its stable rotation, which in turn influences everything from day and night cycles to the predictability of our climate. It's the planet's stable anchor, maintaining equilibrium through its quiet, constant existence. So, the next time you feel the solid ground beneath your feet, remember the hidden world beneath. The Earth's core, an inaccessible realm of unimaginable heat and pressure, is not a dramatic, fiery spectacle. Instead, it is a quiet, diligent powerhouse. It's boring. It's a constant churning of liquid metal, generating a magnetic field that safeguards our atmosphere, and its profound heat driving the geological processes that shape our very continents. It is the ultimate example of a boring astronomical concept that is fundamental to our daily existence, a testament to the unseen forces that quietly sustain our world. Next time on Boring Astronomy, we'll delve into perhaps the ultimate cosmic mystery, a concept that often inspires awe and fear, but which we will explore for its profound, even boring, physical reality. What is a black hole? The ultimate cosmic mystery, explained.